Good morning to all of you. First of all, I want to introduce myself. I am Ankit Acharya, working as an assistant professor in Hasmukh Goswami College of Engineering, Vahelal. And today my content is GTU question paper with solution of June 2010. Up to question number 2A we already seen. So let's start with question number 2B. Right, here is a question number 2B. Show that question number 2B1, show that the set S is equal to e raised to x, x e raised to x, x square e raised to x in C2 minus infinite to infinite is linearly independent. Right, this C2 means the set of continuous function from minus infinite to infinite. Okay, and this question asking 2 marks. Here is the solution. So first of all, just try to understand that how to solve this question. Here we have 3 functions, and to check that the given functions are linearly independent or dependent, we have to find Wronskian determinant. Right, what is Wronskian determinant? That call it these 3 functions as f1, f2 and f3, and you have to find Wronskian determinant. That Wronskian determinant is equal to determinant of f1, f2, f3. The first row is f1, f2, f3. The second row is f1 dash, f2 dash, f3 dash. Right, so derivative of the first derivative of the given 3 functions, and the third row is f1 double dash, f2 double dash, f3 double dash. That means the second derivatives of the given 3 functions. Right, solve this determinant. If that determinant is not equal to 0 for all x, then you can say that the given 3 functions are linearly independent. If the value of determinant you will get 0, if suppose the value of determinant you will get 0, then the given 3 functions are linearly dependent. Okay, so here we have 3 functions: e raised to x, x e raised to x, x square e raised to x. Right, so let f1x is equal to e raised to x, f2x is equal to x e raised to x, f3x is equal to x square e raised to x. f1 dash x, that means derivative of f1. So we know that derivative of e raised to x is e raised to x, derivative of x e raised to x. Right, derivative of x e raised to x, that is equal to, use multiplication rule for derivative. So that is equal to e raised to x as it is, the derivative of x is 1, so e raised to x plus x as it is, the derivative of e raised to x is e raised to x. So you will get x e raised to x plus e raised to x, that can be written as x plus 1 e raised to x. Right, now this is f3 dash x. So here is f3, x square e raised to x. Now how you can find derivative? The derivative of x square is 2x, e raised to x is as it is. So 2x e raised to x plus x square is as it is, the derivative of e raised to x is e raised to x. So e raised to x will be common, and you will get x square plus 2x into e raised to x. Okay, now again you have to derivative of each 3 functions, f1 dash, f2 dash, f3 dash. So f1 double dash x, that is equal to e raised to x, f2 double dash x, that means what, derivative of f1 dash x, that will become that will become the derivative of e raised to x is e raised to x. Now see, x plus 1 as it is, plus the derivative of x plus 1 is 1 and e raised to x is as it is. So you will get x plus 1 e raised to x plus e raised to x. So whenever you will be common e raised to x, you will get x plus 2 e raised to x. Right, similarly f3 dash x, that is x square plus 2x e raised to x. Now derivative of f3 dash x, that is f3 double dash x with respect to x. So derivative of x square plus 2x, that is 2x plus 2 e raised to x as it is, and then derivative of e raised to x is e raised to x, x square plus 2x. So whenever you take e raised to x will be common, in bracket you will get x square plus 4x plus 2, right. So this derivative is quite easy to solve. Now we have to put this all derivatives into the determinant. So here is our determinant, that's w of x, that is called Wronskian determinant. See, the first row is f1 dash x, f1x, f2x, f3x. Second row is f1 dash, f2 dash, f3 dash, and third row is f1 double dash, f2 double dash, f3 double dash. Okay, so put all this value which we already find right here. So put all this value here. The first row is e raised to x, x e raised to x, x square e raised to x. The second row is e raised to x, x plus 1 e raised to x, x square plus 2x e raised to x. Third row is e raised to x, x plus 2 e raised to x, x square plus 4x plus 2 into e raised to x. So now see, in each column you will get e raised to x will be common, right. In each column, see, the first column e raised to x, the second column we have e raised to x, and the third column we have e raised to x. So that e raised to x will be common from each column, right. So that will become e raised to x into e raised to x into e raised to x will be common. That means what? E raised to 3x. E raised to 3x will be common, and in this determinant you will get, now the first column you have now 1 1 1, the second column x, x plus 1, x plus 2, the third column you have x square plus 2x, x square plus 4x plus 2, right. Now how to solve this determinant? Again we can use some process, some row process. So multiply first row with -1 and add into the second row in this determinant. Okay, so multiply first row with -1 and add into the, that means this process, call it r2 minus r1, right, and r3 minus r1. We multiply first row with -1 and add into the second row, and multiply first row with -1 and add into the third row. So you will get e raised to 3x as it is, 1 x square, the first row is as it is, the second row become, see, the second row become 0. See, you multiply first row with -1 and add into the second row, right. So 1 minus 1 0, x plus 1 minus x, right, x plus 1 minus x, that will become 1, x square plus 2x minus x square, that will become 2x. Okay, so 2x, and the third row 1 minus 1 0, x plus 2 minus x 2, x square plus 4x plus 2 minus x square, that is 4x plus 2, right. So here is 4x plus 2. Okay, now again in first column you have only one is a non-zero element, other are 0, right. So if you want to solve this determinant, the value of this determinant is exactly the value of this determinant, because you have first column 1 0 0, right. So if you want to solve this determinant, just 1 into this minor of 1, right, then minus 0 into minor of 0, this 0, and plus 0 into minor of this 0. But whenever you multiply 0 with any value, that will get 0, right. So just the value of this determinant is exactly the value of this determinant you will get. This is exactly the minor of 1. This is exactly the minor of 1. That means just remove this column and this row, right. So you will get 1 2x 2 4x plus 2. So 1 2x 2 4x plus 2, correct. So e raised to 3x into this determinant 1 2x 2 4x plus 2, and that will become you will see 1 into 4x plus 2. So 4x plus 2 minus 4x, that is 2. So the value of this determinant is 2, and e raised to 3x is already in multiplication. So you will get the whole value is 2 e raised to 3x, right. Now this is always non-zero, e raised to 3x is always non-zero for any x, So this function does not have value 0 for all x in minus infinite to infinite. So the function f1 f2 f3 form a linearly independent set. If you will get if you suppose you will get 0, the value of this determinant is equal to 0, then you can say that the given three functions are linearly dependent. Okay, but here that case does not happen. Here we get the value of this determinant is non-zero, right. So I already told you that if the value of Wronskian determinant is non-zero, then the given functions call it linearly independent set, right. So next question, this is question number 2b1. This question asked in 2 marks, right? And next question number 2b, second part. Check whether V is equal to R2 is a vector space with respect to the operations u1 u2 plus v1 v2, that is equal to u1 plus v1 minus 2, u2 plus v2 minus 3, and alpha into u1 plus u2, that is equal to alpha u1 plus 2 alpha minus 2, alpha u2 minus 3 alpha plus 3. So here we have to use this addition and this scalar multiplication. Okay, we cannot use standard addition and standard scalar multiplication for R2, just we have to use this addition and this scalar multiplication to check that the given set is a vector space or not, right? That is the question. So one by one we have to check all the conditions. We know that to check that the given set is a vector space, we have to check total number of 10 conditions. The first 5 conditions are for additions and another 5 conditions are for scalar multiplication. Okay, the first one is closedness, then commutativity, associativity, identity, inverse. So these 5 conditions are for additions. Another 5 conditions, right? Closedness, distributive law, the 2 distributive law, one is associative law, and then identity, right? So there are total number of 10 conditions. One by one each condition we have to check that the each conditions are satisfied or not. If one of the condition is dropped, if one of the condition is not satisfied, then you can say that the given set is not vector space, right? So here is a question mark. Okay, here is a question mark that the given set is a vector space or not. So let's start with one by one each conditions. Let's try to check. Okay, so here is the question. I repeat the question. We have to use this addition and scalar multiplication for vector space V is equal to R2 and check the given set is a vector space or not. So just try to understand carefully that this set addition, how we define that u1 u2 plus v1 v2, that is equal to u1 plus v1 minus 2. That means what? First coordinate plus the addition of first coordinate and then minus 2, right? Just try to understand with this angle. Then addition of second coordinate in both the vectors and then minus 3. Okay, similarly just try to understand this scalar multiplication, that alpha into u1 u2, that is equal to alpha into first coordinate plus 2 alpha minus 2, then alpha into second coordinate minus 3 alpha in plus 3. Okay, so here is the solution. Let's take 3 vectors belongs to R2 where V is equal to R2, u1 u2, u v w, where u is u1 u2, v is v1 v2 and w is w1 w2. So u1 u2 plus v1 v2, first condition u1 u2 plus v1 v2, that is equal to u1 plus v1 minus 2, u2 plus v2 minus 3. Okay, so that is always belongs to V, right? Because of these 2 coordinates are already real numbers, right? V is R2, right? So if any element belongs to R2 means what? They have 2 coordinates and both the coordinates have real numbers. So definitely these 2 coordinates have real number because u1 v1 u2 v2 all are real numbers. So addition and subtraction of any 2 real number, that is always real number, right? So this closedness is already satisfied clearly. This associativity u plus v in bracket u plus v plus w, that is equal to, that can be written as in bracket u1 u2 plus v1 v2 plus w1 w2 outside the bracket w1 w2. Now addition of this 2 vector that already defined with this manner, u1 plus v1 minus 2, u2 plus v2 minus 3, right? We have to use this definition. Just see this definition, right? u1 plus v1 minus 2, u2 plus v2 minus 3 plus w1 w2, right? Again we have to use this definition, this addition which already given in the statement, that first coordinate plus first coordinate minus 2, that means what? u1 plus v1 minus 2 plus w1 minus 2 again, so you will get minus 4, right? So that's why here u1 plus v1 plus w1 minus 4 and then u2 plus v2 minus 3, u2 plus v2 minus 3 plus w2 minus 3 again using this definition, right? Second coordinate plus second coordinate minus 3. So if we use this definition again, you will get u2 plus v2 minus 3 plus w2 minus 3. So that's why you will get u2 plus v2 plus w2 minus 6, right? And that is equal to u1 plus u2 plus V1 plus W1 minus 2, V2 plus W2 minus 3. Okay, and that is equal to U1 plus U2, U1 U2 plus V1 V2 plus W1 W2. So it's quite easy to check that associativity. This is associativity, right? In bracket U plus V plus W, that is equal to in bracket U plus in bracket V plus W you will get. Okay, so associativity is satisfied. Now check commutativity. That means U plus V is equal to V plus U. Let's start with U plus V, that is U1 U2 plus V1 V2, that is equal to U1 plus V1 minus 2, U2 plus V2 minus 3, right, using the definition. Now U1 plus V1 minus 2 can be written as V1 plus U1 minus 2, and again U2 plus V2 minus 3 can be written as V2 plus U2 minus 3. Okay, just replace the U1 V1 and U2 V2, the value the place of U1 V1 and U2 V2, just replace. Now this is called V1 V2 plus U1 U2, right, and that is equal to V plus U. So it's easy to understand that we will get U plus V is equal to V plus U, right. So commutativity, Kramnonium. Okay, now next condition, for any U is equal to U1 U2 identity, just try to check that identity. For any U is equal to U1 U2, there exists theta is equal to 2 3, such that now 2 3 is already belongs to R2, right. U1 U2, there exists theta is equal to 2 3, theta is identity, our identity, such that U plus theta, let's try to check that U plus theta, okay, that is equal to U1 U2 plus 2 3 U1. Now using this definition, addition, using the definition of addition which already given in the statement, first coordinate plus first coordinate, addition of first coordinate minus 2, so you will get U1 plus 2 minus 2, and then U2 plus 3 minus 3. Okay, so U1 U2, that is equal to U, right. So U plus theta is equal to U. Similarly you will get theta plus U is equal to U. So theta is our identity, that theta is equal to 2 3. Next condition, try to check inverse, the last condition for addition, inverse, that for any U is equal to U1 U2 there exists minus U